Hello students, today we are going to understand the concept of signal space and the computation of error probability. So before that, first we will understand what is a signal space. Signal space means a signal which is occupying some space. Suppose there is a transmission of bit 0 and bit 1. So there is a space for bit 0 and there is a space for bit 1. If these two bits will get combined, you will get four different symbols, that is 0, 0, 0, 1, 1, 0 and 1, 1. So these four different symbols will accommodate or occupy different signal spaces. So this is how you can understand the concept of signal space. A very simple example can be also taken, like there is a hotel having 15 floors and every floor is having 15 rooms. So there are 15 cross 15, 225 possibilities for the signals. So 225 signals can be accommodated in that particular space. So likewise, there is a space, and then in that space there are n number of signals which can be accommodated. So signal space, what it does, it basically helps to compute the error probabilities by mapping the digital symbols to points in a geometrical space, allowing receivers to define decision regions. Errors will occur when received signal lands in another symbol region. Like for example, there is a space for bit yes or symbol 0, 0. If the symbol 0, 1 somehow lands in the space of 0, 0, obviously an error will occur. So that is what it is trying to say in the last line. So there are few key concepts for signal space. One is signal constellation. Signal constellation is nothing but a set of points representing different digital symbols. Like a set of you can say in octal number there is a set from 0 to 7. 8 numbers, there is a set. So similarly, there is a set signal constellation where various points can be combined to make a set. Then second is the decision region. Decision region is what? Each signal point has a defined region. Error will occur if signal belonging to different region falls into another region. I just explained you the example, like suppose a 3-bit combination. There are 8 different combinations from 0, 0, 0 to 1, 1, 1. All the 8 different symbols will accommodate their respective spaces. Like there is a space for 0, 0, 1, and if somehow 0, 1, 0 falls in that particular space, the error will occur because that space was actually allocated for the symbol 0, 0, 1. Finally, distance. Larger distances reduces error probabilities. So a very obvious concept, more the distance, less is the error probability. You can also understand with the concept of this diagram. In the first diagram, signals are touching each other, so the error probability is more. Here you have sufficient space to accommodate signals, so error will be less in this region. So from this example, you can understand how distance plays an important role in the error concept. Now we will understand the error probabilities in various digital modulation schemes, and before that, first we will understand what is the probability of error. So now we will see the error probabilities in various digital modulation techniques. First we will see what is error probability. That means probability of how many transmitted bits are corrupted during a transmission. So it can be measured by bit error rate, which is nothing but the ratio of errored bit by total bits transmitted. For example, if 10,000 bits are transmitted, these are the total bits transmitted, and out of that 1 bit is corrupted. So what is the bit error rate? It will be 10 raised to the power -4. This is how you can calculate the bit error rate. It quantifies how often a digital receiver misinterprets a transmitted symbol. This is how error probability or probability of error can be defined. So now we will see error probability of binary phase shift keying, that is BPSK signal. So it is PE is equals to Q root over 2 EB upon N naught, where this PE is denoted by probability of error. EB is the energy per bit, that means we are transmitting the various bits. So one bit contains how much energy. Then N naught is the noise power spectral density, and then this is the Q function, which can be defined by the integral with the limits x to infinity 1 by root 2x e raised to the power minus t square by 2 dt. This is how you can calculate the error probability of binary phase shift keying. As far as quadrature phase shift keying is concerned, that is QPSK. So for the QPSK technique also, this technique is, or this formula is same, because in quadrature phase shift keying what we are transmitting 2 bits, whereas in BPSK we are transmitting only 2 symbols, zeros and ones, and in QPSK we are combining zeros and ones and producing 4 different symbols, 0 0, 0 1, 1 0 and 1 1. So energy per bit will remain same. So that is why error probability of quadrature phase shift keying, that is QPSK, is same as error probability of binary phase shift keying. Okay, so now we will see the error probability in QAM as well as coherent BFSK, that is binary frequency shift keying. So the error probability in quadrature amplitude modulation, that is QAM, can be defined as PV is equals to 2 upon log m over bracket 1 minus 1 by root m Q function root 3 by m minus 1 EB upon n naught, where EB, n naught, PB, all these things we have already understood what are these things. Here m is the number of symbols. M is equals to number of symbols. Number of symbols means, suppose you are using 16 QAM, that means m is equals to 16. If you are using 64 QAM, that means m will be the number of symbol, which is 64. Similarly, in coherent BFSK, that is binary frequency shift keying, our error probability PE is equals to Q function root over EB by n naught. This is half of your BPSK signal. So these are the 4 digital signals and their error probabilities. Okay, I hope you understand the concept of error probabilities and signal space.